So far we've counted a lot of aspects of permutations. We've counted inversions, we've counted descents, we've counted number of cycles, and something else we can count is called a record. Record is the greatest letter you've seen so far if you read the word from left to right. Records are closely related to cycles, and we can see the relation with a bijection called the parenthesis-removing bijection. So since we're doing something that's related to cycles, I left the cycles here from last time. And let's just write down the number of cycles in each permutation. So there's 2 cycles, 1 cycle, 2 cycles, 1 cycle, 2 cycles, 3 cycles. So the distribution of the cycle statistic on S3 is we've got 2 permutations with 1 cycle, 3 permutations with 2 cycles, and 1 permutation with 3 cycles. So 2 of them, 3 of them, 1 of them, just the numbers. Now a record in W, which we'll think of as written in one-line notation, is an index I with Wi greater than everything that came before it. Or maybe we can think of Wi as the record. But anyway, it's the biggest thing we've seen so far. So let's count records in the permutations in S3. So we've got 3, 2, 1, 3, 1, 2, 2, 1, 3, 2, 3, 1, 1, 3, 2, 1, 2, 3. 3 is the biggest thing we've seen so far, and it's the biggest letter all together, so there's 1 record there. I guess if the permutation starts with the largest letter, there's going to be 1 record. This starts with 2, so that's a record, and then 3 is bigger than 2, so we have 2 records. Starts with 2, and then we get to 3, so again there's 2 records. I guess the first letter is always a record. 1 and then 3, so we've got 2 records. And 1 is a record, 2 is bigger than that, and then 3 is bigger than that. So we have 3 records here. So the distribution of the record statistic, so we'll write rec of W to be the number of records in W. So the distribution of this on S3 is 2, 3, 1. 2 of them have 1 record, 3 of them have 2 records, and 1 has 3 records. So it happens to be the same as the number of cycles. And actually it's not an accident. For any n, the distribution of cycles on Sn and the distribution of records on Sn are exactly the same. The sequence of numbers we get counting number of permutations with 1 cycle, 2 cycles, 3 cycles, 4 cycles, etc. is the number of permutations with 1 record, 2 records, 3 records, 4 records, etc. So to see this, we're going to define a bijection on the symmetric group that maps a permutation with k cycles to a permutation with k records. Let's define phi from the symmetric group itself by phi of W equals the standard cycle notation of W with parentheses erased. So for example, if W is the permutation 26187 354, the standard cycle notation, well, it's a one cycle notation, never mind if it's standard. So 1 goes to 2, 2 goes to 6, 6 goes to 3, 3 goes to 1. That's one cycle. We don't have the letter 4 here yet. 4 goes to 8, and then 8 goes to 4. And then we don't have 5 yet. 5 goes to 7, and 7 goes to 5. Alright, so there's the cycle notation of W. Now putting this in standard cycle notation, we look at the largest letters, 6, 8, and 7. So 6 is going to come first, and the cycle containing 6 comes first. 6, 3, 1, 2. And then 7, 5, and then 8, 4. So every cycle starts with its greatest letter, and then the cycles are listed in order of increasing greatest letters. So that means that phi of W equals 6, 3, 1, 2, 7, 5, 8, 4. Alright, so this is obviously a map from the symmetric group to the symmetric group, but I claim that it's a bijection. So we can't have two different permutations W that map to the same place here. And an injective map from a set to itself has to be a bijection. So it's a bijection because we can define the reverse map. So the inverse map is given by 1. Put a parenthesis, an open parenthesis, before each record. In, let's say, V1 through Vn. And then put a close parenthesis before each open parenthesis. Except for the first. And then we put one more closed parenthesis at the end. Alright, so let's say we start with this and we don't know what permutation that came from. So if V is 6, 3, 1, 2, 7, 5, 8, 4. Put a parenthesis before the 6 because that's the greatest thing we've seen so far. And then before the 7th because that's now the greatest thing we've seen so far. And before the 8. And then we put closed parentheses before every parenthesis except for the first one, of course. And then another one at the end. And we can see that what we get is 2, 6, 1, 8, 7, 3, 5, 4. So this map is a bijection, and then one application of this map is that records and cycles are equally distributed on Sn. So by equally distributed, I mean the sequence's number of permutations in Sn such that the permutation has I records, as I goes from all values, from the lowest value it can to the highest value it can. So record has to be at least one, because the first letter in a word is always a record. And then I guess we could have records in every position if we look at the permutation 1, 2, 3, 4 up to n. So I guess it's really I equals 1 to n. And then if we look at the sequence of permutations such that the number of cycles is I. Now there could be one cycle, because 1 could go to 2, which could go to 3, which could go to 4, etc. And then n could go to 1. That would be one cycle. And then there could be n cycles, because 1 could go to 1, 2 could go to 2, 3 could go to 3, and every single letter could be in its own cycle. So to say that two permutation statistics are equally distributed means that these sequences are the same. And the way I'm using the word statistic so statistic on a set is a function f from that set to the non-negative integers. So these were just things that we can count. Alright, so I claim that records and cycles are equally distributed on the symmetric group. So we have records of sigma of W equals number of cycles in W, because the way the parenthesis erasing map works is we write a permutation standard cycle notation, and then when we erase the parentheses, we have the beginning of each cycle is a record in that sequence of letters. So let me write that out. So if W equals W1 through Wn, and the standard cycle notation is, let's say, A1 through first cycle type is, let's say, lambda 1, and then A lambda 1 plus 1 through A lambda 1 plus lambda 2, etc. Then the records in phi of W, which is the permutation A1 through AN, are precisely A1, A lambda 1 plus 1, A lambda 1 plus lambda 2 plus 1, etc. The records correspond to the beginning of the cycles. So there we have it. The number of cycles in this permutation is equal to the number of records in phi of that permutation. Since phi is a bijection, then this sends all the permutations with one cycle to all the permutations with one record, and all the permutations with two cycles to all the permutations with two records, etc. The end.